Okay. So this unit, maybe, if it loads. This unit we're going to be revisiting, relearning, re-talking about the gas laws. Talked about this a little bit in general chemistry, but we're going to go a little bit more in depth this go around. So first of all, when we're talking about gas laws, a very, very important thing that you need to talk about is pressure. So let's just define it really quick. Pressure is basically the force that acts on a given area. So to find pressure, all you have to do is take your force divided by your area. What is force usually measured in? Newtons. Area, lots of different options depending on what object you are measuring the area of. But again, as long as your units all work out, it doesn't really matter what your area is in. Yes, they're all capitalized. Lowercase a is acceleration, right? Lowercase p is momentum. Tanya has her phone on still. Alrighty, so when we're talking about pressure, we need to talk about a few things. So first of all, we have to be talking about a specific area. So whatever container. So like this room, for instance, if all the doors are shut, this is a container. Nothing's coming in, nothing's going out, right? Technically. We could be talking about water bottles. We should be talking about boxes. When you shut it and it's for the most part contained, that can make a container. Secondly, molecules will move around and hit the sides because gas molecules are trying to expand to fill the entire container. So as they expand to fill the entire container, they are moving around and hitting the sides. It's these collisions that are creating the force, and therefore the container has an area for the force to act upon. So if we talk about the equation that we were just talking about, which I should probably change my color. So we just talked about pressure equals force divided by area. Okay, so if we have more area, what do you think is going to happen to the collisions? Right, if we have more area, our collisions are going to be less, right? Which means, what about our force? Because collisions cause the force. So if we have less collisions, we should have a smaller force, right? What if we take this, like your water bottles right now? Your lids are on them, they're sealed relatively, not a whole lot of air is escaping. We can increase the pressure by doing what? How can we increase the pressure in a water bottle? Squeezing it, which decreases the area, right? If you squeeze a water bottle, you're decreasing the area inside the water bottle, right? Okay, so if we decrease the area, if you are really, really, really strong, what would happen as you kept squeezing? Eventually, you would pop the lid off because your pressure is getting so great. Those collisions are getting more and more and more. So this is going to increase your force. This is also why if you shake a soda, all the carbonation starts to come out of solution. As the carbonation starts to come out of solution, we have more and more gas molecules occupying the same amount of space, which is what causes it to explode when you take the lid off. And I know there's not a lot of room to write right here, but... Alright, so we measure pressure using a barometer. This is not exactly what a barometer looks like, but this is how barometers work. Basically, we have, I'll just use these little dots, and we'll call these air molecules. You can't really see air molecules, but we know they're there, right? Because they are pushing down on us right now. That is why as you go further and further down in the ocean, your ears will start to pop because you're under more and more and more pressure. So basically, do you think all of these air molecules are forcing down? Do you think all of them are going down? No. Some are going down. Some might be going up. Some might be going to the side. They're all kind of going in different directions. But some of them are going down. So basically what happens is we have a whole bunch of air molecules all pushing down, and they're pushing down on this bottom tube that contains mercury. So as they push down on the tube containing mercury, it's squeezing it kind of like a water bottle. So where do you think the mercury is going to go as it's being squeezed? It's going to go up this tube, and this tube has like inch markings like you see in a ruler as it goes up. And sea level is 29.92 inches, but we don't care about 29.92 inches, do we? What do you think we want it in? Metric, right? And actually, we want it in millimeters. Okay, so this is equal to 760 millimeters of mercury, because in science, we want the SI unit. The SI unit is 760 millimeters of mercury, or 1 atmosphere. Okay, those are both, can be used interchangeably. And we're going to talk about the units in just a minute again. But that's how a barometer works. So, let's see here. Units of pressure. Let's talk about them. Because there's more than just 2 units of pressure we're going to use. 1 atmosphere is 760 millimeters of mercury. Again, this is the normal pressure at sea level. As you go up in elevation, your pressure usually decreases, so on and so forth. Why does your pressure decrease? You have less air pushing down on you, right? Because you're higher up in elevation. Okay. All right, 1 millimeter of mercury is equal to 1 torr, so that's really, really, really easy to convert between the two. If you have milliliters of mercury, you have the same amount of torrs. That's another unit of measurement. 1 atmosphere is also 101,325 pascals, or 101.325 kilopascals. This is actually very important because we need to use this when we're going to learn some of our equations here in a little bit. When we start doing our gas laws, when we start learning about all the gas laws, we have to make sure that our units match. If our units don't match, you're going to get the wrong answer. So this is very important that you know how to convert between the different units, because usually you're going to be given it in millimeters of mercury, because that's what barometers usually read it as. However, to use the equations, usually we need it to be in kilopascals. So you need to be able to convert between the two relatively easily. Okay. And does everybody remember how to use a conversion factor? It's been a while. But basically, a conversion factor is 2 equal amounts, right? So a conversion factor for this would be 1 atmosphere over 760 millimeters of mercury. Or we could do it the other way too, can't we? We can do 760 millimeters of mercury over 1 atmosphere. How do I know which one to use in my calculation? Depends on what you're trying to get to cancel out, right? What you're starting with. If you're starting with atmospheres, you would want to use the second one, right? If you're starting with millimeters of mercury, you would want to use the first one. All right. Just kind of like a side note, if your barometer drops below 700, usually meaning you're going to have bad weather. So I bet on Sunday before our big snowstorm, our barometer was dropping below 700. And if it drops below 600, you have hurricane strength winds. So just a little bit of fluctuations in the millimeters of mercury, because think about how small a millimeter is. Think about how 60 millimeters is 6 centimeters. Think about how much of a little fluctuation it could be to cause a giant weather change. Okay. All right, so let's do an example. Let's practice and make sure we can convert these. So, in the first example, what is 724 millimeters of mercury in kilopascals? So you always write down what you start with, 724 millimeters of mercury. And I need a conversion factor with millimeters of mercury on the bottom and kilopascals on the top. Does anyone remember what my conversion factor is here? What is it, 325? Okay, millimeters of mercury cancels out. We're left with kilopascals. Now, if we wanted to do this in using 2 conversion factors, because sometimes it's hard for you to see that 1 atmosphere is 760 millimeters of mercury and 1 atmosphere is 101.325 kilopascals. If you wanted to use 2 conversion factors, that's fine, but I don't think did I lose anyone doing that in one step? Nope. All right, so basically you're going to do all this math, and then we need to figure out significant figures. Before I even put this in my calculator, I want to already know my significant figures. I'm only looking at one number. Which number am I looking at? I'm looking at 724 because the other two numbers are just conversion factors and they don't affect significant figures, right? So if you put this in your calculator, we are going to get 96.5472, blah, 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 blah. Anyhow, when you round it to three significant figures, you get 96.5 kilopascals. All right. The next part of the problem says convert this to torrs. Do we need to do any math? No. Why do we not need to do any math? Torrs and millimeters of mercury are 1 for 1. They have the same exact conversion factor. So torrs, 724 torrs, right? Okay, let's do atmospheres now. Not going to erase everything because I'm starting at the same point, right? So we need a new conversion factor. We need one that has millimeters of mercury on the bottom. We need one with atmospheres on the top. Does anyone remember the conversion factor? 760. 1 atmosphere, right? And no, you do not have to memorize these, but you probably will after we use it a whole bunch of times. So all we have to do is take 724 divided by 760. So knowledge is telling us it's going to be less than 1. How many significant figures do we get to keep again? 3. So I'm going to round my answer to 0.953 atmospheres. Easy peasy, right? All right, so just kind of an intro into gas laws, and we're going to spend a little bit of time on pressure because it's very, very, very important. So if you go to my website, anyhow, if you go to my website, there is a simulation that allows you to change how big the container is, change the type of molecules you have in there. You have big molecules, you have small molecules. You can change the temperature. You can change the amount of pressure. You can add more molecules. You can take out less molecules, so on and so forth. So basically, when you go to my website, and it loaded twice because, again, my computer was on break as well. You hit click to run. I'm not going to click it because it'll probably be overloading my computer right now. And you can adjust, again, the size. You can adjust the temperature. You can adjust the type of molecule. What I want you to do is, first of all, just kind of explore a little bit, play around with it, see if you can kind of start to pick up on some trends. And then I have a data table for you to fill out as you explore, and then some questions to